Alright, so I have a fresh install of Ghidra here, and I thought I'd make a video reading the welcome help page. The first two paragraphs are pretty straightforward. I wrote down a study question: what are some of the capabilities of Ghidra? And they say over here, assembly, disassembly, scripting, graphing, hundreds of other features. Sometimes I forget to look into all the features of products like this. Then there's these other paragraphs about 9.1, which is what I'm running here. The minor note was actually interesting to me. Ghidra compiled .sla files are not backwards compatible due to the newly added other space for syscall support. Alright, so here for data improvements, Jesus, scrolls so fast. Data improvements. Bit fields within structures are now supported as a Ghidra data type. Bit field definitions can come from PDP, dwarf, parsed header files, and can also be created within the structure editor. All data type archives delivered with Ghidra have been reparsed to capture bitfield information. In addition, compiler bitfield allocation schemes have been carefully implemented. Full support for bitfield references within this decompiler is planned for a future release. Now, in support of creating bitfields with structures, a new bitfield editor within the structure editor has been added. The bitfield editor includes a visual depiction of the data type byte layout and the associated bits. The bitfield editor simplifies the creation of bitfields within a structure. So system calls, Ghidra now supports overriding indirect calls, call other, P-code ops, and conditional jumps via new overriding references. These references can be used to achieve correct decompilation of syscall-like instructions. So question, what can Ghidra override now? So we got indirect calls, call other P-code ops, whatever that is, and conditional jumps. A new script, resolve x86 or x64 Linux syscall script, has been provided as part of this initial implementation. Future releases will automatically identify and apply system calls for other operating systems and versions. To support system calls, the decompiler follows references into other address space overlays. This allows users to create address spaces on the fly without worrying about conflicts with existing spaces. For example, instructions with a unique calling convention can be properly handled by adding a reference to a custom function signature. Next up is processor specification, a set of tools designed to make processor specifications easier to create, modify, and validate have been added. The tools consist of a context-sensitive SLA file editor, a P-code validation framework, an external disassembler field, and several scripts to make development easier. And to dig down into the SLA editor there, this is a plugin for Eclipse and provides modern editor features such as syntax coloring, hover navigation, code formatting validation, reference finding, and error navigation. The test suite emulates the P-code to automatically validate the instructions most commonly used by the compiler for that processor. Next up is iOS DYLD and Macho format. DYLD, shared cache images extracted from an iOS image, can now be imported in their entirety. A DYLD's embedded dylibs are split into memory blocks, greatly enhancing follow-on analysis. Internal Macho headers are retained and marked up similarly to ELF and PE files, which includes tracking the origin of the program bytes from the initial import binary. For the Ghidra server, this is now requiring the client to use a TLS connection. Oh yeah, I saw that at the top. Let's go down here. The Ghidra server has two additional authentication methods: Active Directory using Cerberus and pluggable authentication modules, that's PAM, using JAAS. To utilize these new methods, you must configure the server.conf file and use either -A1 for Windows authentication or -A4 along with -JAAS. The JAAS mode will require setup of an additional configuration file. Import. When importing files, the origin of all imported bytes can be tracked back to their offset within the original binary source. This change lays the groundwork for exporting back to the original file after modifying the bytes. There are programmer API methods to get the bytes either from the memory block or the underlying original source bytes. To see the original bytes, a memory block can be mapped onto the original file bytes. The source of each memory block within the memory map is shown in a new byte source column. When hovering on the bytes in the program, listing the origin of the bytes at that address are displayed. So a good question to really internalize. Why is it helpful that imported bytes can be tracked back to their offset in the original binary? Well, so the modified bytes can be exported into the original file. It's a pretty cool feature. Next up over here is the decompiler. It now implements a more detailed analysis of local variables on the stack. This change resolves many problems with disappearing structure initialization and incorrect dead code removal. The decompiler now generates fewer duplicate assignments. For example, repeated assignment of the same value to a variable in two branches will now appear before either branch is taken. In addition, the decompiler now recognizes more optimization patterns used by compilers for signed division, resulting in simplified decompilation. Arch64-based binary decompilation will be cleaner due to better handling of zero extensions into larger registers. This improves data flow analysis and primarily affects functions using floating point neon instructions. Renaming a parameter in the decompiler will no longer commit the data types of all parameters, allowing data types to continue to float without getting locked into a potentially incorrect initial data type. Alright, so I added a question to be answered in the future, took a note. In addition, the cumbersome warning dialog for renaming and retyping has been removed, improving your RE workflow. Now, languages, there are many new processor specifications, including Super H4, MCS96, these ones, a user-contributed specification for MCS48, Super H1 2A, and Tricore. The 16-bit x86 processor specification has been reworked to include protected mode addressing, which the NE loader now uses by default. Handling of segmented or paged memory has been updated to use a newer scheme, hiding its complications from decompilation results. The implementation handles the HCS12X paging scheme as well. Now, many improvements and bug fixes have been made to existing processor specifications. We're talking ARM, Arch64, PIC, 68K, MIPS, PPC, JVM. That one's a awesome one. And others. And if you want to see a change history, you can click that. This is under the bug fixes and enhancements section. And that's the end of the welcome page. So you all should be ready to get started now.